Hi there, this is Further Mechanics, Circular Motion Lesson 2. So angular frequency is the same as the angular speed, and I'm just going to show you a couple of new equations and where they come from. So last lesson we used an equation, V equals 2 pi r over t. So that's the straight line linear velocity tangent to the circle from last lesson. And we also had another equation, the relationship between linear and angular speed, V equals r omega. And what we can do is make these equal to each other. So we end up with r omega equals 2 pi r over t. R's cancel, and we're left with a new expression, omega's 2 pi over t. So omega's 2 pi divided by time period. Omega is obviously in radians per second, time is in seconds. And because 1 over t equals f, we've also got a second equation, a second new one. Omega is 2 pi f. Frequency is obviously in hertz, so that's equation 1. Equation 2, if you want to get them written down. Then what I'm going to do is to go back to the table from lesson 1 and show you how you can utilize these new equations to answer the final question, which I told you to have a go at anyway. Okay, let's do that then. Remember to pause at any point if you need to. So here's the table. And the problem, well, we had to figure out the linear speed, but the issue really was figuring out what 45 revolutions per minute meant in terms of angular speed. So 45 revolutions per minute, so we can get, if we divide that by 60, so 45 over 60 will give us the revolutions per second. 0.75 revolutions per second, which is the frequency, 0.75 hertz. Then to get angular speed, as we've just seen, you just do omega's 2 pi f. So 2 pi times 0.75 gives us an angular speed of 4.71 radians per second. Then to get the linear speed, we just do V equals r omega. So that would be the radius of 0.087 times the 4.71 radians per second, which would give you the linear speed of 0.41 meters per second. So if you didn't get that last time, hopefully that's okay now. And then let's move on and we'll do some more practice questions. So as you know, angular speed can also be measured in revolutions per second or revolutions per minute. So, very similar question. Calculate the angular speed in radians per second of an old vinyl record player set at 80 RPM. So if you want to pause and have a go. So first of all, we need to swap the 80 RPM to get the frequency. So that would be 80 over 60, which gives a frequency of 1.3 recurring hertz. Then to get angular speed, we can just do omega is 2 pi f. So it'd be 2 pi multiplied by 1.3 recurring, which would give us an angular speed of 8.4 radians per second. Hopefully that's okay. Let's move on to the next one. So in this question, I want to calculate the angular speed at the surface of the Earth, and then at a distance that's half the radius from the centre. The radius is given below. So if you want to pause and have a go at that, and then I'll take you through the answers. So angular speed at the surface of the Earth is simply given by omega is 2 pi divided by the time period. So that'd be 2 pi divided by the time period is the amount of seconds it takes for the Earth to rotate. So that would be 24 hours. And then there's 60 minutes in every hour and 60 seconds in every minute. So that would give you 2 pi divided by 86,400. So that gives us an angular speed of 7.27 times 10 to the minus 5 radians per second. So the angular speed at a distance that's half the radius from the centre. So part 2. is also 7.27 times 10 to the minus 5 radians per second. Hopefully you didn't fall for, getting that wrong. Omega is just 2 pi divided by time period. The amount of time that it takes this part of the Earth, or this part of the Earth, or this part of the Earth, or this part of the Earth to rotate is 24 hours. The thing that would change, however, would be the straight line linear velocity at these points. And that's just simply because V is equal to r omega. V would be proportional to the distance. Okay, let's move on. So let's have a go at this one. If you want to pause and have a go, then I'll take you through it. What is the angular speed of a car wheel of diameter 0.4 meters when the speed of the car is 108 kilometers per hour? So angular speed, omega is equal to V over r. So what we need to do is make sure that we get V and then r. So V is the 108 kilometers per hour, so we need to turn that into meters per second. So the easiest way to do that is just to divide by 3.6, which gives you 30 meters per second. If you're not quite sure on this one, it'd be 108 kilometers per hour. So we need to turn that into meters per second. So to do that, we would have 108. So meters would be 108,000 meters, divided by the amount of seconds in an hour, 3,600. So essentially we've times by 1,000 and divided by 3,600, which is 30 meters per second. So to shorthand that, you just do, if you've got a speed in kilometers per hour and you want meters per second, you just divide by 3.6. So back to our question. So omega is V over r, so V is 30, divided by the radius. Now be careful because you're given diameter of 0.4, so the radius would be 0.2. So that would give you 150 radians per second. Hopefully that went okay. Let's do one more question. Bit challenging, but let's go for it. So last one. So a model car moves in a circular path of radius 0.8 meters at an angular speed of pi by 2 radians per second. Calculate the displacement after 6 seconds and 8 seconds. So if you want to pause and have a go, and then I'll explain how to do this. So what we need to be wary of, first of all, is the pi by 2 radians per second, like how much angle that is. So pi by 2, well, 2 pi radians is 360 degrees. So pi by 2 is a quarter of that. So pi by 2 is simply 90 degrees. Pi by 2 radians would be 90 degrees. So essentially it's moving 90 degrees per second. And it wants us to calculate displacement after 6 seconds. So if we start at point P and do 6 seconds, so that'll be 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. So this will be our location after 6 seconds. And the displacement is the straight line distance from P to that point. So that would actually be the diameter of this circle. So at 6 seconds, the displacement would simply be 1.6 meters. So 8 seconds would be another 90 degrees, and then another 90 degrees would actually take us back to point P. So after 8 seconds, the displacement at point P from point P is 0 meters. Hopefully you figured that out. Well done if you did. Thanks for watching, and I'll speak to you soon. See you on the next one.